All right, let's jump right in. We're going to talk about a disease that literally shaped history, a condition that once echoed through the grand palaces of Europe, and now, today, that very same disease is at the absolute forefront of a scientific revolution, one that could let us rewrite our own DNA.
You've probably heard it called the royal disease, right? And that's all because of Queen Victoria. Back in the 19th century, she was a carrier, and she passed this genetic mutation down to her kids. And through all those strategic royal marriages, it spread like wildfire into the royal families of Spain, Germany, and even Russia. It's a truly fascinating and honestly tragic piece of history.
But this is way more than just a history lesson. Because today, hemophilia is ground zero for one of the most incredible medical treatments ever dreamed up, a potential one-time cure using gene therapy. And, understanding that long, difficult history is actually key to understanding just how massive this new scientific leap really is. So that's what we're going to do. We'll break down what hemophilia is, how you get it, and how this amazing new science actually works.
Okay, let's start with the absolute basics. What exactly is hemophilia?
So at its core, it's a bleeding disorder that's passed down on the X chromosome, and it all boils down to two key proteins, which we call clotting factors. If your body can't make enough of a protein called factor VIII, you have hemophilia A. If the problem was with factor IX, well, that's hemophilia B. Without these, your blood just can't form a good, strong clot. Now, these two types are not created equal. Hemophilia A is way more common. We're talking about 1 in every 5,000 male births. Hemophilia B, on the other hand, is much rarer, only about 1 in 30,000. It might seem like a small detail, but trust me, this distinction is absolutely critical because the treatment for A won't work for B, and vice versa.
Okay, so one of the first things you probably learned about hemophilia is that it mostly affects men. So let's dig into the genetics and see exactly why that's the case.
It all comes down to our sex chromosomes. Pretty simple, right? Males have one X and one Y, females have two X's. And here's the kicker. The genes that give your body the instructions for making both factor VIII and factor IX are located only on the X chromosome.
So let's play this out. Say a mother carries the faulty gene on just one of her two X chromosomes. For every single child she has, there's a 50% chance she'll pass on that specific X. That means any son has a 50-50 shot of having hemophilia, and any daughter has a 50-50 shot of becoming a carrier just like her mom. Now let's flip the script. What if the father has hemophilia? Well, his one and only X chromosome has the faulty gene. He'll pass his Y chromosome to all of his sons, so it's impossible for him to pass it on to them. But he has to pass his affected X chromosome to all of his daughters, every single one. That means all of his daughters will be carriers.
Okay, but this is where the story gets really interesting because it doesn't just stop with men. There's this huge misconception that women are just silent carriers who don't have any symptoms, but that is definitely not the whole story.
I mean, it seems logical, right? If you've got a backup X chromosome with a perfectly healthy gene, you should be fine. So why is it that a huge number, we're talking 20 to 30% of female carriers, have actual bleeding problems? Some are even as severe as a man with mild hemophilia. What gives?
Well, the answer is this incredible biological process called X inactivation. It's wild. When a female embryo is developing, every single one of her cells makes a random choice. It turns off one of its two X chromosomes. And that choice is permanent for that cell and all its descendants.
And the result of all those tiny random decisions is this. Females are, biologically speaking, a mosaic, a patchwork. Some of their cells are running on the instructions from one X chromosome, and the rest are running on the instructions from the other one.
And you've actually seen this happen in real life, you just might not have realized it. Think about a calico cat. The genes for fur color are on the X chromosome. Those random patches of orange and black fur, that's X inactivation happening right before your eyes. So for a woman, if by pure chance most of her liver cells, the cells that make clotting factor, happen to switch off the healthy X, her factor levels can get dangerously low.
So, knowing all this, how have we actually treated this disease over the years? I mean, the journey has been nothing short of remarkable, moving from just putting out fires to preventing them altogether.
For a long time, treatment was totally reactive. You'd only get an infusion of clotting factor after a painful bleed had already started. Then, things got smarter. The standard of care shifted to prophylactic therapy, getting regular infusions 2 or 3 times a week to keep your factor levels up and stop bleeds before they even begin. Huge step forward. More recently, we got these amazing non-factor therapies, basically engineered antibodies that do the job of the missing factor. And all of that progress has led us here, to the ultimate goal, a potential one-time fix with gene therapy.
And this is it, the breakthrough that could change everything. A single treatment that offers the hope of a functional, long-term cure.
So, how on earth does it work? Well, it's pretty ingenious. Scientists take a harmless virus, called an AAV, and they basically hollow it out. They turn it into a tiny delivery truck. Then they load that truck up with the correct working copy of the factor VIII or factor IX gene. You get this as an IV infusion, and the virus naturally travels to the liver. Once it gets inside the liver cells, it unloads its cargo, and suddenly those cells have the right instructions to start pumping out the missing clotting factor, all on their own.
And the results, they're just staggering. We're talking about patients who used to have dozens of painful bleeds every single year, and after just one infusion, the average number of bleeds plummets to less than 1 a year for Octavian and Hemgenix. That's not just an improvement, that's a completely different life.
But, and you knew there had to be a but, a revolutionary cure comes with a revolutionary price tag. The one-time cost for some of these therapies is $3.5 million. That makes it one of the most expensive medical treatments in the entire world.
So that brings us to the very complicated reality of where we are right now. We had this absolutely incredible technology, but it's not a simple fix for everyone just yet.
Which leads us to the billion-dollar question, or I guess the $3.5 million question. Is this the perfect, permanent cure we've all been hoping for?
Let's just lay it all out. On one side, the hurdles are huge. That cost is, well, prohibitive. A lot of patients also have pre-existing antibodies to the virus we use, which means that therapy just won't work for them. There's a risk to the liver, and we still don't know for sure how long it's going to last. 5 years? 10? A lifetime? We just don't know yet. But on the other side, the hopes are just as massive. It's a one-time treatment. It almost eliminates bleeding. The improvement in quality of life is off the charts. It is truly the closest thing we have ever had to a cure.
And that leaves us with this final, really powerful question to think about. Hemophilia might be one of the first diseases we're tackling this way, but it definitely won't be the last. We are standing right on the edge of a brand new era in medicine. What does our future even look like when a single injection can fundamentally rewrite a person's lifelong genetic story?